Welcome to our series on essential concepts and terminology in transportation planning. In this lecture, we will explore the fundamental concept of the transit assignment. Let us begin by reviewing the concept, characteristics, and classification of public transportation. The most fundamental difference between private automobile travel and public transportation lies in the traveler's autonomy of choice and the continuity of movement. Private automobile users can freely choose when to depart and which route to take. As a result, they usually travel directly from door to door with relatively uninterrupted movement. In contrast, public transportation is a public service operating according to routes and operating schedules established in advance by public agencies or transit operators. Consequently, travelers must accept operational constraints that do not exist in private automobile travel, including walking to transit stops, waiting for vehicle arrivals, and, when necessary, making transfers. These characteristics distinguish public transportation from private automobile travel. The fundamental role of public transportation is to achieve economies of scale by consolidating individual travel demand while at the same time ensuring citizens' basic right to mobility. According to Vucic, public transportation can be broadly classified into two categories: transit and paratransit. Transit refers to services operating with fixed routes, fixed schedules, and fixed fare structures, such as urban rail systems and city buses. In contrast, paratransit refers to services whose routes or operating patterns can be adjusted in response to users' requests. Demand responsive transport, or DRT, is a representative example. Whether taxis are included in paratransit varies depending on national regulations and the classification adopted by individual researchers. In Vucic's framework, public transportation serves as the broader concept encompassing both transit and paratransit. In this lecture, we will focus specifically on transit assignment. Because transit systems operate with fixed routes and fixed schedules, waiting time and transfers become major components of travel impedance that influence route choice. Consequently, transit assignment requires analytical concepts and modeling approaches that differ substantially from those used for highway traffic assignment. Transit assignment requires a much more complex analytical framework than highway traffic assignment. The primary reason is that it must explicitly account for additional components of travel impedance, including access time, waiting time, and transfers. Let us first consider highway traffic assignment. Travelers can depart whenever they choose and travel to their destination in a relatively continuous flow. Transit travel, however, is fundamentally different. In addition to the access time required to reach a transit stop, passengers must endure a discontinuous process, including waiting for a vehicle to arrive. Waiting time involves not only the physical time spent waiting, but also the psychological burden associated with the uncertainty of vehicle arrivals. Furthermore, when no direct service is available, passengers must make one or more transfers. Transfers involve additional walking and waiting, resulting in both time losses and psychological inconvenience. Consequently, transit assignment must consider not only in-vehicle travel time, but also access time, waiting time, transfer time, and the various forms of disutility associated with these components. These elements are converted into a common measure of utility and are represented by a single integrated indicator known as generalized cost. Ultimately, the objective of transit assignment is to model travelers' route choice behavior based on generalized cost and to reproduce actual transit travel behavior, including waiting and transfers, as realistically as possible. To perform transit assignment, it is essential to first construct an accurate transit network as the fundamental input. In Lecture 2, we discussed the components of a transit network in detail. Here, we will briefly review only those elements that are directly related to transit assignment. A transit network is constructed by overlaying transit-specific information, such as nodes, routes, and segments, on the underlying highway network. Transit nodes contain not only geographic coordinates, but also various service-related attributes, including access time, waiting time, and transfer time. An important consideration during data entry is to clearly distinguish between manually input values and those calculated automatically by the software. Transfer time typically comprises the walking time between stops and the waiting time for the next vehicle. However, in most commercial travel demand software, the average waiting time is calculated automatically from the service headway. Therefore, to prevent double counting, only the pure walking time between stops is usually entered into the transfer field. Additionally, a transfer penalty is typically added to reflect the perceived disutility associated with the act of transferring. Next, each transit route contains operational information, such as the route ID, the sequence of stops along the route, service headway, and vehicle capacity. A route consists of a series of connected segments. Each segment contains information such as its length, in-vehicle travel time, and fare-related attributes. Therefore, segment lengths should accurately represent the physical length of the actual transit route. In addition, passenger boarding and alighting are usually represented by an average dwell time, which is an important component of the total travel time. In summary, transit assignment uses this network information to calculate a generalized cost that integrates travel time, fares, waiting time, transfers, and various perceived disutilities. Depending on the transit assignment method being applied, the model then determines the route that travelers are most likely to choose and assigns the corresponding OD demand to that route. This is the fundamental principle of transit assignment. Highway traffic assignment and transit assignment differ fundamentally in both their analytical objectives and their units of analysis. Highway traffic assignment focuses on evaluating whether roadway capacity is sufficient to accommodate vehicle demand. Accordingly, it uses the passenger car unit, PCU, as the basic unit of analysis. Because travel time increases as traffic volume grows, equilibrium assignment models, such as user equilibrium, are required to capture the interaction between traffic demand and network performance. In contrast, the primary objective of transit assignment is to estimate how many passengers use each route or vehicle in order to evaluate service levels and operational efficiency. Therefore, the unit of analysis is person trips rather than vehicles. Traditional transit assignment models often assume that in-vehicle travel time remains essentially unchanged even as passenger demand increases. Admittedly, when vehicles reach capacity, some passengers may need to wait for the next vehicle. However, traditional transit assignment generally does not explicitly incorporate these capacity constraints. Under this assumption, link costs remain independent of passenger volume, making equilibrium concepts such as user equilibrium unnecessary. Consequently, the all-or-nothing assignment method has traditionally been used as one of the basic analytical approaches for transit networks. However, the all-or-nothing assignment is based on the deterministic assumption that all passenger demand is assigned to the single path with the lowest generalized cost. In reality, travelers heading to the same destination often choose different routes depending on waiting time, transfer convenience, and individual preferences. Therefore, while the all-or-nothing assignment can be appropriate for simple transit networks with few alternative routes, it cannot adequately represent traveler route choice behavior in complex urban transit systems with multiple route and transfer options. These limitations motivated the development of the optimal strategy and stochastic transit assignment models, which provide more realistic representations of passenger route choice behavior in transit networks. The all-or-nothing assignment method discussed earlier has an important limitation. It cannot adequately represent passengers' actual boarding behavior when multiple transit routes serve the same stop, nor can it properly account for the average waiting time associated with service headways. To overcome these limitations, Spiess and Florian proposed the optimal strategy model in 1989. The equation shown on the screen represents the mathematical formulation of the optimal strategy model. Although the formulation appears complex, its objective function is strictly convex. Consequently, given the same input data, the model always guarantees a unique solution for link passenger flows, regardless of who conducts the analysis. This property provides objective and consistent results for evaluating transportation policies. The optimal strategy model assumes that passengers do not wait for only one specific route. Instead, they choose a strategy consisting of several attractive routes. the set of routes that minimizes the expected total travel time to the destination by considering both the expected travel time and the service headway of each route is called the attractive set. Passengers are then assumed to board the first vehicle that arrives among the routes included in this set. The algorithm calculates the arrival probability of each route from its service headway and distributes passenger demand among the routes in the attractive set in proportion to those probabilities. One important point should be emphasized. Although the optimal strategy model treats vehicle arrivals and waiting time probabilistically, it is not classified as a stochastic route choice model. It considers only the physical uncertainty associated with vehicle arrivals and service headways. It does not represent behavioral uncertainty, such as travelers' preferences or perception errors. Therefore, the model remains fundamentally deterministic and shares the general limitations associated with deterministic approaches. Stochastic transit assignment was developed to overcome the deterministic assumptions of the optimal strategy model. Rather than assuming that all travelers make identical decisions, stochastic models represent unobservable factors, such as travelers' preferences, levels of information, and imperfect knowledge of the transit network through the concept of random utility, thereby providing a more realistic representation of route choice behavior. The most widely used approach in practice is the logit-based model. Logit models are based on the independence of irrelevant alternatives assumption, which states that the random error terms associated with different alternatives are mutually independent. In highway traffic assignment, overlapping routes create correlations among these error terms, leading to the well-known path overlap problem. To alleviate this limitation, extended models such as C-logit and path size logit have been developed. Unlike highway assignment, transit assignment is generally based on transit routes rather than individual highway links. As a result, the path overlap problem is often less severe than in highway networks. However, when multiple transit routes share long common segments, or when alternative routes are highly similar, the limitations of the IIA assumption may still become significant. In such cases, applying correction models such as C-logit or path size logit is desirable. Nevertheless, because of its computational efficiency and ease of implementation, the standard multinomial logit model remains the most widely used approach in practical applications. Another important challenge in logit-based modeling is constructing a realistic choice set consisting of the alternative routes that travelers are actually likely to consider. Including too many alternatives may introduce unrealistic paths and reduce the behavioral realism of the model, whereas including too few alternatives may fail to capture actual route choice behavior. Consequently, constructing an appropriate choice set remains one of the most important practical issues. Modern transportation software typically uses k-shortest path algorithms to generate behaviorally realistic alternative routes for route choice analysis. In summary, stochastic transit assignment uses logit-based models to represent travelers' perceptual uncertainty and behavioral diversity, thereby providing a more realistic description of route choice behavior. Consequently, the optimal strategy model is generally efficient for relatively simple transit networks, where service headways and average waiting time are the primary sources of uncertainty. In contrast, stochastic transit assignment is more appropriate for complex transit networks, where travelers' preferences and behavioral uncertainty play a more important role. The optimal strategy model and stochastic transit assignment discussed earlier are both frequency-based models, meaning that they use service headways rather than the actual departure times of individual vehicles. Consequently, they cannot explicitly represent timetable information or capture time-dependent travel decisions. For example, travelers may choose to wait for a vehicle that departs later if it enables them to reach their destination earlier, rather than simply boarding the first vehicle that arrives. To represent this type of behavior, schedule-based transit assignment was developed. With recent advances in automatic vehicle location technology and the widespread availability of real-time passenger information, travelers can now monitor vehicle locations and expected arrival times in real time. For example, if passengers know that an express bus arriving a few minutes later will reach their destination sooner than a local bus arriving now, they may deliberately allow the first bus to depart and wait for the express service instead. Schedule-based models were developed to represent this type of time-dependent route choice behavior more realistically. These models construct a time-expanded network based on the actual timetables of individual vehicles and explicitly represent both vehicle movements and passenger movements over time. Consequently, even for the same origin and destination, the optimal route may vary depending on the departure time. This ability to analyze time-dependent route choice is one of the distinguishing features of schedule-based transit assignment. Despite these advantages, several practical challenges remain. First, accurate timetable data and reliable real-time operational information are essential. Second, it is difficult to fully represent operational uncertainties such as service delays and unexpected disruptions. In addition, as the temporal resolution becomes finer, the size of the time-expanded network increases rapidly, resulting in substantially higher computational requirements. Nevertheless, major transportation planning software packages have continued to enhance their schedule-based transit assignment capabilities. These models are particularly valuable for analyzing highly reliable, schedule-sensitive transit systems, such as railways and express bus services, as well as travelers' route choice behavior under real-time transit information. The all-or-nothing and static assignment models discussed earlier are all explicitly formulated mathematical optimization models. Because these models satisfy mathematical properties such as the convexity of the objective function and guarantee a unique solution, they provide objective and consistent analytical results whenever the same input data are used. In contrast, real-world transportation systems are inherently dynamic and often too complex to be represented completely by mathematical equations alone. In such situations, simulation is widely used to reproduce real-world traffic phenomena as realistically as possible, rather than to derive an analytical optimum. Instead of solving a single mathematical equation, simulation defines behavioral rules for travelers and vehicles and repeatedly executes those rules to simulate how the state of a transportation system evolves over time. In this sense, simulation is fundamentally a rule-based analytical approach. To better understand the concept of simulation, consider the problem of estimating the area of a geometric shape. The area of a regular shape, such as a rectangle or a circle, can be calculated exactly using mathematical formulas. However, the area of an irregular shape cannot easily be determined by a single equation. One common solution is the Monte Carlo method, which estimates unknown values by repeatedly drawing random samples from probability distributions. For example, if a large number of random points are generated within a rectangle containing an irregular shape, the area of the shape can be estimated from the proportion of points that fall inside it. Traffic simulation follows the same principle by repeatedly generating stochastic events, such as travelers' departure times and route choices, and evaluating many different scenarios. Because simulation incorporates randomness, the results may vary slightly from one simulation run to another. Therefore, transportation analysts generally evaluate system performance using the average or expected value obtained from multiple simulation runs, rather than relying on a single result. Increasing the number of simulation runs improves the statistical stability of the results, but also increases the computational burden. Consequently, analysts must balance statistical accuracy against computational efficiency. Recently, rapid advances in computing power, mobile big data, and artificial intelligence have made it possible to analyze transportation systems with a level of realism that was previously unattainable. Looking ahead, transportation analysis is expected to increasingly combine mathematical optimization models and simulation in a complementary manner, providing more realistic analyses and supporting more scientific and data-driven transportation decision-making. Recent advances in smart card data and mobile location data have brought transit analysis into a new era. In the past, travel behavior had to be estimated from relatively limited travel surveys. Today, however, passive mobility data, which are collected automatically without requiring any response from travelers, enable analysts to observe actual transfer locations and route choice behavior for nearly the entire population. These large-scale datasets are expected to advance transit assignment in two major directions. The first is the refinement of stochastic transit assignment models. Large volumes of observed travel data now make it possible to calibrate the utility functions of logit-based models with much greater precision. As a result, travelers' sensitivities to waiting time, transfer time, and in-vehicle crowding can be estimated more accurately, significantly narrowing the gap between analytical model predictions and actual travel behavior. The second is the advancement of AI and agent-based simulation. By learning from massive behavioral datasets, AI can identify complex decision-making patterns that are difficult to represent using conventional analytical models. This enables more realistic simulations of individual traveler responses under conditions such as major public events or unexpected system disruptions. Despite its high predictive performance, however, current AI still has limitations because its internal decision-making process often remains a black box. Fortunately, rapid advances in explainable AI, or XAI, and causal inference are gradually overcoming these limitations and making AI a more reliable tool for transportation planning and policy analysis. Ultimately, transit assignment will evolve beyond the simple allocation of travel demand and become a key component of a transportation digital twin, where big data, AI, and agent-based simulation are fully integrated. Such a digital twin will provide a virtual environment in which various transportation policies can be evaluated before implementation, serving as a core platform for developing data-driven transportation policies and supporting more scientific and rational decision-making. Thank you for watching this lecture series on concepts and terminology in transportation planning. In the next and final lecture, we will conclude this series by exploring transportation project evaluation, one of the most important topics in transportation planning. Thank you for watching. I would love to hear your thoughts or comments on today's lecture. If this explanation was helpful, please like and subscribe to support this series.